Okay, so let's provide some guidelines for the method of variation of parameters. So in the first step, let's look at the problem, okay? So the typical problem for which this is applicable is a problem in which the non-homogeneous term, again, is in the form of a function of t times a function of x. And as the first step is to find the eigenfunctions xn of x of the homogeneous problem. So either you remember what they are, or you just solve it briefly. I mean, you find the separated, find the Sturm-Liouville problem, and figure out the eigenfunctions. And one main property that needs to happen, which it happened in the previous case, is that when you take the double derivative of those eigenfunctions, you should end up with some constant, which may depend on n, times the same eigenfunction. So remember from the previous example, when we took the derivative of sine of nx twice, we ended up with minus n squared sine of nx. So that's one essential property that needs to happen. Then we're going to, in the second step, you're going to assume that the solution is going to be in the form of a summation of these eigenfunctions, with an of t to be determined. Second step, you're going to write f of x, which is this part of the non-homogeneous term, in the format of the same series. So let's say f of x is bn times xn of x. So some series representation in terms of the same eigenfunctions. And by the way, I forgot to mention here, the boundary value problem to begin with will have some initial condition, right? So u of x0 would be some function, let's say h of x. And at this point, you also need to get h of x, that initial condition, in terms of the same series representation, whether it's sine, cosine, depending on the case. So let's say h of x is dn xn of x in the summation. In step number 3, you're going to plug in all of this stuff into the PDE. So take the solution format, plug it into the PDE. So partial t would be summation an prime of t xn of x. Partial x twice will be an of t, and like I said, let's say xn double prime will be cn xn of x. And then finally g of t, and plug in the summation corresponding to f of x. So as in the example done before, if you combine everything on the right-hand side, you should end up with a summation of the same eigenfunctions. Which will allow you to extract the ODE that provides you a way to solve for an of t. We're going to do that immediately. Remember, that ODE in an of t will have an initial condition itself, which comes from the initial condition of the problem to begin with. So plug in that format for your x of t into the initial condition. So we're going to replace t with 0. So that gives me an of 0, not of t, an of 0, xn of x, and then match it with the series representation for h of x, which I denoted by dn, summation of dn xn of x. And that will give you an of 0. So finally, the last step, let's call it step 4, will be to actually solve the initial value problem that gives you an of t. So an prime of t equals a squared cn an of t plus bn g of t, and then an of 0 will be dn. So this could be easier or tedious, really depending on these Fourier coefficients. And of course, what gn of t is. I should emphasize, though, that, again, it's not actually overly difficult because lots of these guys are constant, right? So although this could be a tedious term, cn and dn, this is just a constant, a squared times cn. So when you set up those two integrals, I1 and I2, to solve the first order ODE, those integrals are not, I mean, the first one at least is not that bad. The second one, it depends on what g of t is. And of course, the initial condition could be also tedious depending on how dn looks like, but that's also a constant. So if we look at the overview of the method, again, two things are essential for it to work. The non-homogeneous term should be in the separated form. The eigenfunctions of the homogeneous part of the problem should have this property, that if you differentiate it twice, you get, and most of, that's going to be true in all the problems basically we encounter. And in particular, it's true for sine and cosine. And that allows you to essentially take this format of the solution, and when you plug it in, you end up essentially with a big summation in xn of x, which allows you to match the coefficients in t. When you do that matching, that leads to an ordinary differential equation in the coefficient to be determined. And the initial condition for that ordinary differential equation will come from imposing the same format of the solution into the initial condition in the problem. So you will need two Fourier series in this problem. One, like before, for the initial condition, one for f of x, that part of the non-homogeneous term. So with that, give it a try with similar problems on the homework, and I'll see you next time.